Hi, my name is Arash Sheikhlar, and in this talk, I'm going to present my team's theory of autonomous cumulative transfer learning. What we call transfer learning is the agent's ability to apply its prior knowledge to new circumstances, to new situations. And those new situations should be similar to some extent to the agent's past experiences. The main requirement of transfer learning is autonomy, which means that a cognitive agent has to do knowledge transfer on its own, without any intervention from the outside. The agent uses transfer learning to expand its knowledge efficiently and apply that to relevant situations. In fact, transfer learning is useful for knowledge accumulation in a systematic way. It is also helpful for the agent to create and initiate the actions that are relevant to the task goals. Transfer learning has different meanings in different contexts. It is good to notice that there is an important difference here between transfer learning's definition in cognitive science and what has been called as transfer learning in narrow AI's community. In cognitive science, transfer learning is the usage of previously acquired knowledge and skills in new learning or problem-solving situations. Thereby, similarities and analogies play a crucial role in knowledge transfer. In narrow AI, however, the things are different. Transfer learning in deep neural networks depends on a human programmer that chooses higher layers of a pre-trained network and reuses them to train another network in a similar domain. And this is done by the programmer's sense of what should be transferred. Besides, in transfer learning methods of reinforcement learning research, there is also a human programmer that trains a learner on a specific task and reuses that learner in another task which is similar to the first task. But what we call similar here is nothing more than the human's sense of similarity, which means that there's a human that uses his own intuition for choosing the so-called source and target tasks in reinforcement learning. The main issues of narrow AI transfer learning methods is that they do not have autonomy, which means that they cannot transfer the relevant knowledge on their own. Besides, they cannot make analogies and learn from them. They're not able to find the differences and similarities between the tasks and the situations the agent may encounter over its lifetime. Therefore, those methods do not seem to be promising for achieving general intelligence. For an effective transfer learning method, which is able to make analogies and transfer the most relevant knowledge to a situation, we need a cumulative learning mechanism, which is able to unify the new input information with its existing knowledge over time. Cumulative learner is able to measure the match between input information and existing knowledge. And the overlap means that the agent is familiar to some aspects of the new information, the new knowledge. And this is critical for analogy that the agent is going to do in the next steps. The reason behind why this mechanism is called cumulative is that it is able to unify the new and the old information, and at the same time it selects a suitable knowledge to the situation with an eye to its existing knowledge. If it turns out that the similarity detection was wrong, it will be inspected and learned from, which means that the cumulative learner enables the agent to improve its analogy-making capabilities over time. For cumulative learning, we need a framework, which is causation. Assuming that the world is following the rules of causation, a cognitive agent has to have the ability to extract those causal rules. Extracting the causal rules or causal relations needs logic, and the logic can steer the knowledge accumulation process. It enables the cognitive agent to make predictions, do planning, and transfer its knowledge in a more effective way. And that logic has to be non-axiomatic, which means that it relies on experience gathered by the agent over time. It also needs to be ampliative, that is, it contains four main elements: deduction for making predictions, abduction for doing planning, induction that enables the agent to generalize its rules and its models. And the last but not least is analogies, that is used for adapting the acquired knowledge to new situations. It is good to take note that Bayesian models are not adequate for this picture. I mean, the Bayesian transfer learning models might work in general predictions like the ones that exist in Solomonov's theory of universal induction. However, they're not adequate for extracting causal relations. According to Judah Pearl's Tech Report, in probability theory, the distributions are static, while causation and causal factors like taking the actions can change all the distributions, and in fact, doing and taking actions by the agent or even external disturbances is the thing that is not considered in Bayesian framework. And so there's no point in fusing Bayesian and causal calculations. Our theory of autonomous cumulative transfer learning, or ACTL, is relied on three main concepts, and it is good to define them first, then we can start talking about the theory itself. We have a phenomenon, which is a process or occurrence or an object that contains many aspects, and those aspects are subdivisions of the phenomenon that have importance for the agent goals. And we have percepts, which are sets of variables that are generated by the sensors or constructed through the agent's imagination. Our theory of autonomous cumulative transfer learning, or ACTL, is based on prediction. It says that if the agent can predict a particular aspect of a phenomenon using its prior knowledge, then that aspect is familiar to the agent, and therefore it is non-novel. If the agent can make correct predictions for all important aspects, we can say that the phenomenon is completely familiar to the agent. The ACTL assumes analogies regarding variables, their values, the importance of those variables and their values, and the dynamics between the sets of variables and their associated values. An example of such a mechanism is ERA, that was constructed based on a proto-version of the ACTL theory and demonstrated to be capable of learning highly complex tasks. ACTL relies on similarity calculation, and we will see that the similarity argument verifies the validity of ACTL theory. And in fact, we will see that the similarity and the familiarity concepts are working together since the amount of familiarity can be determined by the accuracy of the agent's predictions. And the similarity thresholds, or I would say distances, can be calculated by the abduction, or what we call backward chaining. Similarity is a function that compares two sets of knowledge. And here we can see that the first set of knowledge is a part of the agent's knowledge base, and the second set of knowledge is the knowledge that is relevant to the aspect. And using these two, we can compute the familiarity. Our argument from similarity is based on the following dimensions: variables, states, relations, and transitions. And the relations and transitions are between states. State similarity in cardinality of variables is the first dimension of similarity, and it is defined between two states, and it can be found by taking the intersection of their variables to all variables. Obviously, it's a number in between 0 and 1, and therefore if it is greater than 0, those two states share variables, and therefore they can be compared. The next dimension is the state similarity in important variables. This gives us a set of important variables over which a gradient may be computed using a gradient function, which sorts the variables into a list from least important to most important, and this gives us a set of sorted variables based on the importance. Based on the importance. SSVI is defined as the ratio of important variables to shared variables. So it's a number in between 0 and 1. And if it is greater than 0, it means that the states share at least one important variables, and therefore they are relevant. The threshold of importance is computed when the comparison is done and may therefore be different at different times. A minimum set of important variables would be those that are directly referenced in the goals for which the similarity is being computed. And as I mentioned in my first slide about why we should have transfer learning, analogy making is significant for choosing actions. So whether similarity is high enough for an agent to base its actions depends on a lot of factors, including a risk-benefit analysis, conflicting goals, and etc. But how relevance can be determined? Relevant knowledge in our theory is retrieved based on the goals of comparison. Since explicit goals must be defined by referencing particular variables and their values, the important variables for the comparison are already known. And reasoning from the goal, which is called backward chaining or abduction, will help us identify the relevant prerequisites. Then the next dimension is variable similarity of proximity for two identical important variables in two states with different values and times. The variables have temporal proximity if their time difference is less than a threshold, and they have value proximity if their value difference is less than a threshold. And those two thresholds are computed in the same way as the threshold for the importance of the variables was computed. In relational similarity, the causal relations between the states are compared. If the causes are similar regarding cardinality, importance, or proximity of their variables, there's a state similarity in causes, or SSC. If the effect states are similar, we have a state similarity in effects, or SSE. We can conclude that if two states have both SSE and SSC, their transitions are similar. In other words, if a causal relation holds between two states, like S1 and S2, it is required to check if a third state, which is S3, has SSC with S1. If so, the same prediction is made with the hope that it will reach to another state, which is S4, that has SSE similarity with S2. If the prediction is correct, then we can say that S1 and S3 have state similarity in transitions, or they have SST similarity. Let's assume that a percept as the first state has SSC, or state similarity in causes, to a cause part of a model as the second state. Then the agent will make the same prediction as what it knows as a transition for the second state. If it turns out that the prediction was wrong, that aspect is not familiar. This is the main source of negative transfer learning, in which the agent thinks that the state is familiar, and so it makes a prediction, and then it finds out that the prediction was incorrect, which means that the state is not actually familiar. It just looks familiar. According to this argument, a cumulative learner stores its knowledge in the form of causal models. It observes sets of variables and values and compares them to its cause-effect models. It finds the SSC similarities and makes the related predictions. Then, if there is an SST, it generates new causal models while storing them for the later use. We also have an argument from the empirical results we got from narrow AI learners implementation. We collected the data from the implementation of a deep reinforcement learner called actor-critic on card-pull task. We will see that this learner is not able to do transfer learning since there is no mechanism for causal relations extraction. This can be considered as a counterexample of a true cumulative learner, and therefore it supports our theory. Here we go into the details of it. After training the learner on the card pole's normal mode, the forces are reversed. So the only change is the inverted left-right forces. As you can see, it takes more than 1,000 epochs to relearn the second phase of the task, which is more than twice the learning rate of the first phase. This shows that the actor-critic cannot do transfer learning, although all the variables and their values except the force are the same in both first and second phases. Even after reversing the forces again to default mode in the third phase, again it takes more than 500 epochs to learn. We can conclude that the actor-critic cannot find the importance of the variable, of the force variable during its lifetime, and it cannot extract the causal relations. Also, there is no analogy making mechanism in actor-critic. One of the results of ACTL theory is that we can divide all the aspects of a phenomenon into two sets, which are set of novel aspects that the agent fails to predict, and the set of familiar aspects that the agent was successful in prediction. And we can find the set of novel aspects by subtracting the familiar aspects from all aspects of a phenomenon. The other results of ACTL theory is that the knowledge of familiar aspects are stored as new causal models. These familiarity-based new models are useful for generating other new models. The new models are variations of previous ones through which the agent made the prediction. We should notice that the new and the old models have similarities, but they are not the same. They have differences, and therefore there is a similarity distance in between. So what we call similarity has direct relationship with the difference between the new and previous models. Familiarity and similarity are codependent, and each of them plays a significant role in calculating the other one. Similarity gives the agent the ability to compute which aspects should spawn which predictions. Then, familiarity determines the similarity distance between the new and the old causal relations. The amount of familiarity to a phenomenon increases as the agent continues dealing with the phenomenon by observation, making predictions, and taking actions on it. And taking actions as a critical step requires energy and time. Therefore, we need models that consider time and energy, in which the transitions capture the forces involved in the phenomenon. The final conclusion we can get from the ACTL theory is that since increments in familiarity are equivalent to novelty reduction, our notion of familiarity might be used to guide the learning process, which enables the agent to make better predictions and improve the goal achievement. Finally, we can conclude that if an effective analogy-making mechanism exists, the agent will be able to make better and more accurate predictions, and this provides higher capability of transfer learning. We believe that our ACTL theory and its results open the door to numerous research possibilities in transfer learning research that can be done in the future. Among them, it is good to build a cumulative learning-based system like ERA and evaluate the transfer learning capabilities of that. We should also take note that the transfer learning needs to have solid ways of evaluations. And we hope that ACTL gives the researchers good metrics for that. Finally, since relevance must be computed by backward chaining or abduction, doing research in this particular area will be very promising. Thank you for listening.